we are making some exciting improvements in the technology, and we will be describing those changes in the Ignite conference that is coming up in May. But I understand not everybody could go to that conference, and I would be happy to come back and present those contents along with my colleagues in this chapter. So I really look forward to that. So as Ami was saying, I've been with SQL Server for a long time. I've been working here for 12 years, and all of my time is in SQL Server. I've been mostly focusing on storage side. So I've done like the bulk load things and snapshot isolation stuff and compression. That was a big deal for us. Then I was involved in a very serious way with always on readable secondary and offloading backups with the secondary stuff on that side. Then I moved to in-memory OLTP, and that was a pretty exciting release for us in 2014. And we continue to make significant improvements based on the customer feedback, and you will see some of those exciting changes coming in the next release of SQL Server. And now I'm focusing on the column store technology for the last 12 months. So the session today is on SQL 14 in-memory OLTP. And what I was going to focus on is, I don't know how many of you have used in-memory OLTP or have attended any sessions on that. So for now, I'm not assuming anything. I'm just going to give you a very high-level overview of what in-memory OLTP is all about, and then do some simple demos to get you a feel what it means to manage a database which has in-memory tables as a DBA. So assume you are a DBA and I give you a database which has multiple in-memory tables. So the question is, what can you do? How do you manage it? How do you monitor it? So that's pretty much the focus of this presentation. And my hope is, once we are done with the session, you will understand that in-memory tables, even though they are part of the same SQL Server database, they have a different kind of structures, both indexes and how they are stored, and their persistence, the way we manage their persistence is very different than what we are used to with the traditional SQL Server tables, which are based on the pages. And we are calling traditional SQL Server tables as disk-based tables, and we are calling the memory optimized table or in-memory tables as memory optimized table. So sometimes people get confused in the sense, if memory optimized tables are not disk-based, what does it mean in terms of persistence? So I think there is a confusion in terms of name, but when I say memory optimized table, they are optimized for access inside the SQL Server memory, but they are persisted just like your traditional disk-based tables, okay? And then we will also go into how the memory is managed for this memory optimized table. One of the key things to note would be that in a disk-based table, we bring the data into buffer pool as needed, right? Because when I'm running a query, we go through an index and say, okay, I need these pages, these rows. We bring them into memory on demand. And of course, as those pages become old or not needed, they get moved out of the memory. So the key point is the data for disk-based tables does not reside or live in the buffer pool forever. It is demand-based, which is different than memory optimized table, which has a strict requirement. This is, I'm going to say it again, a strict requirement that the full content of memory optimized table must be in SQL Server process memory. So those are the key things, and let's just walk through that. So in-memory tables are relational tables. So they are no different. They are relational tables. They have rows. And since we have optimized these tables for in-memory residency, in the sense we optimize the query execution using the fact that these tables are in memory. Okay, so it has a different row format which is optimized for memory. And other interesting thing is they are not stored in pages. So there are no 8K pages, if you will, for memory optimized tables. You can think of memory optimized table in a very simplistic way as the rows that are scattered. Scattered is the wrong word, but I think they're just in the memory of SQL Server process, and they are held together. I mean, they are bound together through a index. So they're not pages. I mean, if you have a heap in disk-based table with no indexes, SQL Server using the page manager, you can say, tell me all the pages allocated to this table, and I can go through those pages and look at the rows, and I can get all the rows in the table, right? But here there are no pages, so the rows are bound together with an index. That means you must have at least one index for memory optimized table. Otherwise, we will not be able to bind them together. So that is something interesting. Other thing that we have done, which is I think very significant, is we do not use locking. We are using optimistic concurrency control both for reads and writes. And the reason I wanted to emphasize reads and writes, if you recall, with 2005 onwards, SQL Server has provided a snapshot isolation and read commit snapshot, which is an optimistic concurrency control and non-blocking concurrency control. But if I was running a DML transaction under a snapshot isolation or read commit snapshot, they still take the locks. But with memory optimized table, there are no locks. So when I modify a row, insert a row, I do not take a lock, right? So then the question comes, how do I achieve the consistency in the isolation across transactions? And it is not the topic for this presentation, but what we do is we track all the rows that were modified by concurrent transactions. If there's an overlap in terms of those rows, one of the transactions is chosen as a victim and it is aborted. Now, it may seem that this is a significant issue because transactions getting aborted just because they had the same data set. In a traditional system, they would have blocked, right? I mean, transaction 1, if had a exclusive lock on a row and somebody else wants to update, it would have blocked, but not with in-memory OLTP. They would have proceeded without knowing that the transaction 1 has been modifying the row, and in the end we figured out the conflict and one of the transactions is rolled back. Now, the reason this is not a significant issue is in a traditional OLTP environments, you do not see the conflict between the rows. I mean, on the same row. I mean, those two transactions do not commonly modify the same row. What you see is they are accessing rows that are sitting on the same data page, right? So what happens is I have transaction 1 is accessing row 1, which is on page 1, and transaction 2 is accessing row 2, which is also on page 1. What happens is when they want to modify, only one transaction is allowed using a mechanism called latching, which is a physical lock on the physical structure. So what happens is if multiple transactions are modifying row in the same physical page, you will see some sort of a bottleneck because of latching, because only one guy is allowed at one time, right? Now, since there is no pages for in-memory tables, there is no latching as well. So I think one of the key things to walk away with is that the locking, there's no locking, there is no latching, and SQL Server achieves the isolation levels that are defined in NC SQL using maintaining these row sets using optimistic concurrency control. And I think this is a full presentation on its own, but I think that's at a very high level. Now, in terms of indexes, right, I mean, there is only one kind of index available in the disk-based table, which is a B-tree index, right? You can define, of course, a cluster index or a non-cluster index, but it is a B-tree index. With memory optimized table, we have a new kind of index, which is we call a hash index. What hash index is, essentially you organize the rows in the hash index by hashing the key, and any row that maps to a given bucket in the hash table, you put them in that bucket, and those rows of course are linked. So you can have, on a given hash bucket, you can have multiple rows if there was a collision, right? So that's how the hash index is organized. Now the hash index is very useful if I'm just searching for a query predicate. So I can just hash on the key and I go to the bucket, and assuming there was no collision, you can find the row right there, right? So it's a very, very fast path to get to a row if you were only doing the equality search, right? But hash index is not suitable for the range index. For the range index, you want to say, give me the rows that are greater than certain value or is between certain things and so on and so forth. So for that, we have another implementation of a range index. Actually, this is a sticky point. Should we call it it's not clearly a B tree because this is a different implementation. So we call it as a non-cluster index, which is optimized for range searches. So this is almost like a B tree in the sense you can do the query saying give me greater than range and whatnot, but different implementation. And also it is implemented using non-blocking protocol. So we do not do any locks. When you split the page, when you do whatever, nothing is going on in terms of locking. So you might have heard I just said page and said, hey, you said there is no page for the memory table, and why are you saying page? So the index pages are index data, like the rows and the pointers to the rows from the index structures. Those pointers are organized in pages, so that's the only paging part that is there in the memory optimized table. And we do not latch those pages. So this is very, very different. And again, I said that's a different presentation, so that's something good to know. Okay. Now, other non-intuitive thing is that we do not persist the index contents. We persist, of course, the schema of the index. I mean, if you create an index on column C1, it is an index on column C1, but we do not persist the index on disk. We only keep the index in memory, right? Because all the data lives in memory, index lives in memory. So now what happens when I say shut down my SQL Server for whatever reason and I restart? So the data, like all the data for the in-memory table, has to be loaded into memory because it has to live in memory. And we build the index as the data is getting loaded. And so one would think, hey, that means the recovery will take a long time, which sounds, reasonable, because not only you're loading the data, you are also building the indexes. But what we found was the way we have created these indexes, we are almost, in many cases, able to load the data at the speed of I/O. So you can load data if you have 16-core machine. You can load data from disk storage into memory 16-way at the speed of I/O. I mean, of course, you have more CPUs. You can load more. So you can load the data at the speed of I/O while building the indexes. So that's what we have seen. And in some cases, of course, you have a lot of indexes. It will make it more complicated, but that's what it is. So there is no index persistence, which means you're not logging any changes to the index. Now, this is a very important point, because imagine this, right? If you have a table, a disk-based table, and you have, say, 4 indexes, when I insert a row into the table, I do one log record for the data that I inserted. Then I have to have 4 inserts, one for each index. I'm writing 4 more log records. So each insert is like 5 log records. With the memory optimized table, the only thing I'm doing is I'm inserting the row into the table, and that is logged, but none of the index structures are logged. Very important point. And finally, I mean, the disk index fragmentation is a common thing. I mean, I hear all the time people say, hey, my index is getting fragmented, my query performance increasingly slows down because, over time, because fragmentation increases, I have to defragment my indexes and so forth, and so on. Now, with the memory optimized table, indexes are in memory, so there is no like a fragmentation from the disk perspective, right? It is, yes, of course, in the memory, the index pages or index pointers will be distributed in the memory. Maybe there will be some NUMA angle to that, but it's a very different. So there is no fragmentation from a disk perspective. So that is on the structures. Now, if you look at the row, so we have a row header, and then there's a payload, which is the columns. Now, if you look from a semantic perspective, even the disk-based tables have a row header, and then you store the column. So that thing is not any different, right? So that's how it looks like. But the row header is different, of course, and the payload is different. So what we have is, this is actually two very important columns. Header has a begin timestamp and an end timestamp. And what begin timestamp tells you is the transaction timestamp that inserted the row. So it's important. When you imagine this, when you're running transactions in an OLTP system with memory optimized table, each transaction that is doing any operation in the memory optimized table is given a monotonically increasing timestamp. All right. So start with timestamp 1, 2, and on and on. So what it says is that begin timestamp, that this row was inserted by a transaction that is a timestamp, begin timestamp. And the end timestamp tells you that this row was deleted by a transaction, that timestamp is so. So clearly the begin timestamp and end timestamp is the life cycle of the row. Okay, the row exists in the system for that duration. Now what happens when I update a row? When I update a row, SQL Server for memory optimized table, it deletes the row and then inserts it. So update is a delete, insert. So the end timestamp and the row will be inserted, and it will have a begin timestamp, right? And then a row that exists, which has not yet been deleted or updated, has the end timestamp, which is infinity in the sense it is the current row. That's how we look at it. Other thing to note is that the index pointers, because ultimately, right, when you have an index, you have to point to the next row, right? For example, in a range index or even in a hash index when you have a collision. So these pointers, there is one pointer for each index. We support in 2014 up to 8 indexes, which is actually quite a reasonable number for OLTP databases. So these pointers are the pointers that I'm showing you here. These are one pointer chain for each of the indexes. That's how it is. So let's look at how the structures looks like. Okay. So I think we talked about this one, and I'm going to come back to this later. But I want to show you the row, how they look like. Let me just talk about that because I think it is related. So we already talked about that the data has to stay in memory, and currently what we are saying is the size of memory optimized tables within a database, we recommend it to be equal or less than 256 gigabyte. So that's the size we are supporting in 2014, and in 2000 or the next version of SQL Server, we will relax this significantly, but for now it is 256 gigabyte. Now people say, well, 256 gigabyte, I have an OLTP database that is 1 terabyte, how will it work, right? Good question. The point is, we are saying to our customers, in fact this is a design, that you do not have to move all the tables in your database to in-memory. We only want to move the tables that are performance critical, because we can give you up to 30x performance improvement. It's not 30%, it's 30x, 30 times, significant gain. And in fact, these numbers are not something that we are in the test lab. We have seen these numbers with our customers as well. So real life workloads are running with a huge amount of performance gains. So what we are saying to our customers is, you do not move all the tables, but move the tables that are performance critical. Now the question comes, how do I know which tables are performance critical? Well, a lot of DBAs who have been working with those applications, they already know which tables are the cause of scalability bottleneck or performance bottleneck. So they already know, and they can move those tables to memory optimized table. But what we provide in 2014 is a tool that comes with Management Studio, which can analyze the workload and can tell you which tables and which stored procedures are most suitable for in-memory migration. So the key point I'm making is that only a subset, hopefully a small subset of those tables, you have to move to memory optimized table. So the 256 gigabyte limit is not as bad as it may seem in the beginning. But like I said, this is something we have been hearing from our customers. And one key point that customers say is, okay, today my data can fit memory optimized tables are less than 150 gigabyte, they're fine. But tomorrow if I go beyond 256, what happens? I can't really rewrite my application or change my application that quickly. So people want an assurance that if my in-memory tables indeed go beyond 256 gigabyte, there's a way for me to handle it. And I think the way we're going to support is we will allow a much larger size for a memory optimized table. I mean, these days, if you buy boxes, I mean, getting a couple of terabytes in the box is not that uncommon, and then people can say, okay, I'm going to add more physical memory and I'll be fine. So that's that. The other thing that is important is like memory optimized table take a lot more memory than your disk-based table because everything has to be in memory. So how do I control how much memory will be taken by memory optimized table? Right? Now you can say, well, I mean, I need what I need, right? But the point is, you may be running your SQL Server in a consolidated environment where you have multiple databases, and you don't want a misbehaving application impacting everybody else. That's one example. And also, like the difference in the memory optimized table versus non-memory optimized tables is, once the memory is given to memory optimized table, it holds on to it. It is very greedy about that. I mean, it cannot give it away. If it give it away, that means I'm removing some rows, right? So it cannot lose the data. It holds on to that memory. Of course, if you delete the rows, those rows become garbage, and we will do garbage collection. So what happens is, if the memory optimized tables grow, they may eat into physical memory of SQL Server process to an extent that SQL Server becomes non-operational, because SQL Server needs memory not only for storing the rows, it needs memory for many other things, right? Like managing a lot of structures. So the key point is, we want to bound how much memory is taken by memory optimized tables, and we provide a existing way, which is a resource governor. What you can do is you can say, I'm going to bind my database to this resource governor, and I'm going to give this pool. So I'm going to create a pool using the resource governor functionality. I'm going to map my database within memory tables to that pool, and I'm going to say that pool has 40% or 50% or 60%, whatever suitable for your environment, that much memory. That means the rest of the memory is available for all other things. So we have a very strong recommendation that you start a memory optimized table by binding it to a resource pool. Now, we touched upon that when you delete a row or when you update a row, the row becomes a garbage after some time, right? So it needs to be removed, because if it is not removed, it is consuming memory in your system. So how does a garbage collection work, right? So clearly we talk about updates and deletes, and so if you imagine this, right? If I had 10,000 rows, I'm just giving a very, very simple example, 10,000 rows. You update 10,000 rows, all of them. So now suddenly you got 20,000 rows in the system, right? 10,000 of those are stale because they are deleted, and the 10 are the new. So the question really is, we are doubling the memory consumed by these tables. So the garbage collection job is to figure out those rows that have been deleted. How do I collect them? How do I free up the memory in the background? And so that is very important, because if you don't do that in an efficient way, you will run out of physical memory, even though your active data is not really that large. So the garbage collection mechanism is different than what we have for row versioning based isolation levels that we had starting 2005. But the fundamental concepts are very, very similar. And in this slide, this one and next one, I want to explain how the garbage collection works, right? So the garbage collection that we are doing for memory optimized tables is actually quite a unique design. And let me describe 5 properties that are important in this context. And I think I want to emphasize those properties strongly. The first one is non-blocking. What it means is that the garbage collection is continuous. We keep collecting garbage rows as they are getting generated. There is no periodic, like you can think of a checkpoint. Like let's say checkpoint happens after every 5 minutes. I'm just making this up. So it's not the garbage collection that runs every 5 minutes, because if it runs periodically, then at the time when it is running, you will see a lot more CPU impact because garbage collection is going on. So your workload may see some sort of fluctuations. So what we have done for memory optimized garbage collection, it's non-stop, it is continuous, it is always happening. So it's non-blocking from that perspective. Now, second thing is it is cooperative. what cooperative means is the garbage collection job is not assigned to some thread. Like I'm going to give a simple example. Like if you think of like the checkpoint thread or the dirty page writers or whatever, those have a dedicated job of doing that, right? Okay. With the memory optimized tables, the garbage collection actually is done by user transactions once they have committed their transaction. So this is actually important. So what happens, say this, I'm running a transaction and the transaction commits, right? So once the transaction commits, the CPU or the core that transaction was running at could be freed up, and if the batch exists. The key point is when the transaction is done, before that CPU is released, what we do, we look at the work, garbage collection work. Are there any rows to be garbage collected? So before this thread gives up the CPU, it will go and process all those rows. So basically, user transactions at the end of their transaction commit, they will do some garbage collection work. So the user transactions are indeed doing the garbage collection, but there's a thread in the system which is we call garbage collection thread. It is creating the work for these guys. So that guy's responsibility is look at all the deleted rows and put them in some structures, and we're going to look at that structure. And these user transactions, when they finish, they say, is there any work for me to do garbage collection? I can do some garbage collection. So it is distributed. Now, so that is interesting, and it is efficient in the sense, and efficiency is like when I'm scanning a row, and I'm going to show you through a visual, it becomes more clear. When I'm scanning a row as part of a transaction, then let's say I'm scanning the row through a hash index, and I find a row that is to be garbage collected. So what I can do is I can delink, I can remove that row from that index because I know that that row does not need to be read because it is garbage. So it is efficient in the sense I'm taking care of garbage work as part of normal transactional activity as I'm accessing the structures. And it is responsive in the sense it responds to memory pressure. So suppose the garbage collection has generated, the user transactions have created so many deleted rows, and I'm running into memory boundaries. So at that time, SQL Server will go into high gear and do aggressive garbage collection. So the point is, it is very responsive to the memory pressure. If there's no memory pressure, doing the garbage collection is not that critical because you would rather spend time on the user transaction, stuff like that, and there's no reason to do extra work there. So the garbage collection is indeed responds to memory pressure, otherwise it stays in the normal course. And finally, it is scalable in the sense, and like I was saying, if only user transactions are creating garbage, right? So as more and more transactions are running in the system, there are more workers for you who are going to do the garbage collection because each user transaction has to do some garbage collection. So it's a self-throttling mechanism. More transactional activity, more garbage collection, and then, so you will never have a situation, at least from a design perspective, that the garbage collection is falling behind, things should happen. Okay, so that's that. Let me explain to you from a user perspective what happens, right? Here what I'm showing you is a typical in-memory structure of some table, which has, in this case I'm showing 4 rows, and it has 2 indexes. One is the blue index, which is a hash index on name, which is on the left side, and then you see a hash index on city. And what you see is, remember these pointers, the red pointer and the blue pointer, these are the pointers from within the rows. I was showing you the row structures. I mean, these are those pointers, right? So from the index, I have a pointer to the row, that bucket, and then the rows that are linked to that bucket are here. So for example, if I look at the number 2, on the blue side, I have 2 rows that map to the same bucket, right? And so on. So this is on the name. So for example, Jane is here, the John is here. So now one interesting thing about the timestamp, this is something we talked about. So 50 comma infinity means that this row was inserted by a transaction of the timestamp 50, and is n timestamp is infinity, that means this row is not yet deleted. This is the current row. If I do a select star on this table, I should see this row. Now the next row you see is 100, 200. What it means is created by transaction timestamp 100, removed by transaction timestamp 200. So if I'm running a transaction with the timestamp say 250, I should not see the row with the timestamp 100 to 200 because that row was removed by a transaction 200, right? This is like a snapshot isolation. So that's how it is. So now let me show you one more interesting thing, right? Here you see the John row, right? You see the only difference you see is the Prague versus Beijing in terms of city. So this row actually was updated in this case that John was say living in Prague and he moved to Beijing. So you can see the row was updated by transaction 200. So it is marked as delete, right? And then a insert. So that's how you see it. Now let's assume for simplicity that SQL Server knows that the oldest active transaction in the system has a timestamp of 250. That means all transactions with a timestamp lower than 250 have either aborted or committed, right? So what can happen is if I do a select now, I do a select star from table where name is John. So SQL Server Optimizer will choose the index on name as the index to run this query, right? So I come here and notice I'm going to go back. Notice as the query execution comes here and it finds this row and says, well, this row is garbage, right? Because it has the timestamp of 200 and oldest active transaction is 250. What it will do is it will remove the link to this row. So it just, there's no blue link anymore to this row, right? It just goes to this guy and it points out, it returns one row for this predicate. Now the thing is, even though I remove the row from the blue index, it is still linked on the red index, right? Now when the row has to be garbage collected, the John Prague has to be garbage collected, it has to be removed from all the indexes it is connected to, and then the row has to be removed. So what has happened is the user transaction, the select query that I ran, it took care of one part of garbage collection work, which means removing the index link it was traversing. So it removed that link, it reduced the work that needs to be done ultimately by garbage collection. So I can imagine if this row was linked by say 5 or 10 indexes, all those indexes are being traversed. So some of those links will be removed as part of normal transactional activity. You do not have to access that index, especially for garbage collection, right? So this is what we talk about in an efficient. The garbage collection is efficient. So this is what's going on, right? So let's say the select statement is done, and ultimately these rows will get garbage collected, right? Because transaction commit time, after the transaction has been committed, we can do some garbage collection, and these garbage rows will be removed, and you'll be left with these two rows which have the timestamp and timestamp of infinity. So this is how actually it works. Now on that note, let me show you a demo of memory management. And one thing I know, I just noticed the time is 10:40, so I have literally 20 minutes to finish everything. So I will mostly focus on the memory part and briefly touch upon the storage. So let's do this. Let's what I did here, I already created a database. So I'm going to show you here. If I go to the database, you will see in-memory OLTP database. So what I've done is I created a resource pool that you see here, and pool I am in-memory OLTP, and I said max memory percentage 20%, which means the memory allocated to SQL Server process, I'm only going to give 20% to it. I have already created the pool. To show you that, I'm going to go to I'm going to show you this. Why I'm not seeing it? Hold on. I see. Just a second. Open, I'm going to file, and I want to show the resource pool. I want to show you the memory DB. I want to do this thing. Okay, so let me just bring those scripts up, and I'm going to make it wider. So if I want to show you the resource pool, I can do this query. And what it shows you is that I've created a resource pool and it got 20% of the max memory, and you can compute. This is how it is allocated right now. So now what I'm going to do is I'm going to map my database to it. The database is already created. So what I'm going to do is I'm going to bind this database to the pool. So the database has been bound. Now one thing I need to do, I can actually even check the binding. I can run this command, and this says that database ID, which is the in-memory OLTP database I just created, is mapped to this resource pool. Now the interesting thing is, in order for this binding to take effect, I mean many people miss that step, you have to take database offline and online. So I'm going to go here, and I'm going to take it offline, online. Let me do that. Okay. The reason I did that was when you take a database offline, it removes the database from the memory, right? So if it was a memory optimized database with memory optimized tables, when I take it offline, all the memory allocated has been freed up. And when I bring it online, it will map to the pool that I wanted to map it to. And the reason is, it is possible that before database was mapped to a different pool, and you want to map it to another pool, so you can do that way. Or if you do not map your database to any pool, by default, or when you create it, it goes to the default pool. So SQL Server has two pools that are created automatically. One is the default pool and one is the internal pool. So if you create a memory optimized table in SQL Server, it will be mapped to default pool. So any rows that you insert will be coming from the default pool. And now if you create a user pool, the name pool, and you want to map a database to that pool, so now if we did not do offline online step, then some memory will be coming from the default pool and some will be from the named pool. And currently we do not support that configuration. So what you need to do is take the database offline and then bring it online. All right. So now I have mapped the database to the pool. Ami, I'm not sure if there are questions, but if there are questions, you can ask me. I'll try to respond. So I'm using the database, and now what I'm going to do is I'm going to create a table. I'm creating a memory optimized table. So let's just look at it here. So I'm creating an index which is non-clustered index. This is a range index that I'm creating, and there's a hash index that I'm creating, and I have a primary key on it, right? And in this case, I said durability schema only, which means I do not want the data of this table to be durable. This is not the default option. The default option is schema and data, which means not only you persist the schema, you also persist the data. So let me create this table. Other thing about this table is that if you look at the size of the table, is approximately 8K. The reason I chose this number because it just makes it easy to compute the memory consumed and so on and so forth. Okay, so I create the table. Now let me go to a DMV. This is new DMVs that we have created for memory optimized tables. Let me run this guy, and then I'm going to show you the memory taken by this table. Okay. So what it shows to me is that I have this table, and currently it is not taking any memory, right? Memory allocated is 0, use is 0. This is for the data rows, right? However, for indexes, we have memory allocated. Now, why is that? I mean, there is no row. If you know your traditional SQL Server, when you just create an index, it just takes one page, one IAM page and one data page or index page, right? So how come we are allocating 8 megabyte or more memory for an empty table? And the reason is that, let's go back to the table definition. What you will see is I have said a hash index and the bucket count is 1 million. Bucket count basically means the size of the hash table. It's a very traditional computer science concept for a hash table. Each bucket entry is 8 bytes, so 1 million entries, it becomes 8 megabytes, right? That makes sense? And similarly for the non-clustered index is a little different, which is a range index. It grows and shrinks with the table, but the hash index is fixed in size, so it is fixed at the create time. So that's why we are taking some memory, okay? So now what I'm going to do is I'm going to insert 1,000 rows. When I insert 1,000 rows, see, it became so fast. I insert 8,000 rows. So 1,000 rows of size 8K, that means I'm allocating approximately 8 megabytes, right? So let me go back to the DMV and show you how much memory I'm taking. And you will see it is taking approximately 8 megabyte here. Now memory allocated is different, right? So this is something we should touch upon a little bit. So when SQL Server allocates memory for memory optimized table, it does not do one row at a time, in the sense it gets a memory object from the memory manager of SQL Server, which is of course much bigger than 8K, and then it is just doling out the memory for these tables from that, right? So the memory allocated is larger than the memory used, right? That makes sense? Okay. So we so far so good, right? So we did that. Now let me do some more operations. So I go here, and if I do a select star on this table, I'll see 1,000 tables. Now let me do this. I'm going to delete all the rows. Okay. Now when I delete all rows got deleted. Now one time, sometimes people think, hey, I just delete the rows, I should get the space back. And if I look at the DMV, I go back here and I run it. Notice I still have those rows. So the rows have not been removed. So what you see here is that rows are, if you look at the physical structures of these rows, you will see the timestamp, the begin timestamp and end timestamp, right? You will see all those things, and they are garbage. And they're not yet garbage collected because there is no memory pressure, right? So it's just sitting there. And of course, the more user transactional activity, there is a periodic main garbage thread that what it does, I think it wakes up every minute. And if the number of transactions goes through some minimum threshold, let's say 10 or what, I think it is 10, it says, okay, now I'm going to look at all the rows deleted and I'm going to figure out which I can garbage collect. So that's how it happens. But in this case, I just deleted all the rows, and so the garbage collection has not kicked in. Okay. So now let's do something else. What we will do, I'm going to insert 100,000 rows. Okay. And the way I'm doing it is I only gave 20% of my memory to memory optimized table, and what you will find is when I run this query, I'm going to run out of memory. Right. You see that I got into an error. And actually, I should run no count on. I will do it later, but I think basically what you see is that I ran out of memory, which is expected because I did not allocate enough memory for my workload, right? And when it happens, all inserts and updates will fail, right? Okay. So now let me see how many rows did I insert. If I do a select count star on this table, you see 38,000. I inserted 1,000 before, so that means I ran out of memory after 37,000 rows. Okay, I ran out. What I can do now? I can increase my resource pool from 20% to 40%. And notice this you could do online. You can monitor the memory taken by SQL Server, memory optimized tables, and if you think you are running out of memory available to your database, you have multiple choices. You can add more physical memory to the box, give more memory to SQL Server. And also you can increase the pool size of the pool that was mapped to the database, right? So now what I'm going to do is I'm going to insert another, I doubled the pool, right? So I'm going to insert 130,000 rows. So I'm just doing another 30,000 rows, right? I'm just going to insert that. And now it should succeed because I doubled the size of my pool, right? And you will see it succeeds. So everything got succeeded, right? Now if I do a count star on this, I should see 68,000 rows, right? 68,000 rows I got. Now let's do something interesting. Let's delete all the rows. I'm going to delete all the rows. I'm just doing in a loop because I want to give some time for the garbage collection to kick in. So I'm deleting all the rows. So as we talked about, not every row will be garbage collected. Now the things have been deleted, and if I do a count star, I should not see any row because this transaction that I'm running, it is running at a timestamp when the transactions that deleted the row have committed, right? So it should not see any row. So this is the correct behavior. Now I'm going to go and insert 50,000 rows. All right. Now if the garbage collection had not happened, I will run out of physical memory. But what happens is when I'm inserting rows, system is getting under memory pressure because I'm inserting more and more data. And what will happen is in the background, the garbage collection will happen, and this thing should succeed. I should be able to insert 50,000 rows, right? Now, so this is the thing I wanted to show you about the garbage collection. And one thing that is very interesting about the garbage collection is this. You can monitor how the garbage collection is happening. And I'm going to show you something very interesting about the garbage collection. I think this is one thing that you need to see. So this is a very useful DMV, which is XTP GCQ stat. So what is a queue? So basically, I'm running on a 4-core machine in my laptop. So there are 4 schedulers that are running user transactions. So what happens is the main garbage thread is responsible to queue up work on each of those CPUs. Okay, I'm not using the word CPU, but it's a core, right? Each of these CPUs. And any transaction that is running on that CPU, after it commits, before it gives the CPU away, it sees, are there any garbage collection that I need to do, and it will do that garbage collection and move on. So what you see here is that on this queue ID 0, there were 1097 garbage collection work items that were enqueued and 1097 were dequeued. That means they were the garbage collection work that was enqueued, and then those were also processed, so they have been dequeued. So there is nothing, no garbage collection to be had right now. So that means garbage collection is keeping up. If what you see is a current queue depth is increasing and increasing, is not getting, it's not decreasing, that means the garbage collection is not going on. So in this case, I think it shows that garbage collection indeed go through. All right. So this is what happened. Now what I'm going to do is I'm going to show you. Actually, I'm going to stop here. I'm going to go back to my presentation, and I want to show you, talk about something about the storage.
Sunil, do you have time for a couple of quick questions?
I do.
Okay, so let's see. Rakesh asks, what is the tool called in 2014 for identifying memory optimized objects?
Right. Okay, so we have a, I actually am blanking out. So with the Management Studio SSMS, there is I think I'm just blanking out of that name. This tool I've used so many times. So it is, Rakesh, if you send me mail, I'm going to respond to you. It's a, yeah, it's a tool that comes with the Management Studio. You can start it. It will start collecting the properties of the characteristics of the workload, and based on that, it will tell you which tables will qualify for memory optimized. So I'm sorry about that.
That's the Management Data Warehouse report, right?
SSMS. Yeah, SSMS.
Okay. Another question by Madhu. How much of extra CPU we need to consider to make sure in-memory OLTP works efficiently?
Okay. So, Madhu, this is a great question. So, what we found was that data, since it is sitting in memory, we can efficiently execute the transaction with very few instructions. So, I'll give you an example. Let's say you have a employee table, disk-based table, and that's just a big table, very big table, and you have a index on employee ID. And for now, assume everything is in memory. Assume all the employees, everything is in memory, right? Now, if I ask you a query, if I ask a data query, select star from table employee, where employee ID is, say, 10. If it is a good database design, and if it is a common query, you will obviously have an index on employee ID. So the way SQL Server will execute that query would be, it will go to the root page of the index, right? And look at the page and say where's the next link and so on. If the index tree itself was a depth of 4 or 5, that means you have to traverse index tree 4 or 5 pages, latch, search, find the next pointer, on and on, right? And then if it was a non-cluster index, which is possible, then it has to traverse the cluster index, which could be another 4 levels, and then finally goes to the row, right? So a lot of instructions are taken in terms of searching these pages, latching, removing the latch, and so on. With the memory optimized table, I go to the hash index, to the employee ID, and I find the row right there, right? So the number of instructions taken to execute the same query is much, much lower. So what we find is the amount of CPU that you had before you had memory optimized table, let's say you were taking 60% CPU. when you move to memory optimized table, I'm making a very blanket statement, you will see order of magnitude reduction in the CPU utilization because we're not running as many instructions. In fact, in some cases, we have seen 20x reduction in the CPU time. Now that means now you can run more workloads. So in fact, on the same box, after they migrate the tables, the critical tables to memory optimized table, you can get a order of magnitude better throughput without upgrading the hardware. This is actually a very important point. So to answer the question in a very roundabout way, so what you should see once you migrate the data to the memory optimized table, your CPU should go down significantly.
Okay, great answer, Sunil. Thank you.
Sure.
Just a reminder, we have 5 minutes to go.
That's fine. That's fine.
So
I'm going to wrap this up. I'm not. Yeah.
Okay, I think we had enough questions for today, so you can wrap up your presentation.
Okay. So what I'll do is I'm not going to go through the storage part because there's no time. So the memory usage, our basic rule of thumb is that when you configure your memory optimized table, just allocate, make sure you have twice the memory that you would need for your tables, just to account for garbage collection, stuff like that, okay? And for index data, we talked about that. You have hash index, so you need to account for the size taken by the buckets. And also for the non-cluster index, it grows and shrinks with the table. So it has the index key and the pointer. So you have to account for these things. In terms of configuration, we strongly recommend mapping the memory optimized tables to a named pool at the database level. And you should monitor how the memory is being consumed, garbage collection, and so on. So in many cases, all these things happen automatically, but what happens is customers who are migrating to memory optimized table for the first time, the usage pattern is quite different. So it's a very important idea to monitor and get comfortable with the whole thing. I think that's where I will end because I did not have time to go to the storage, but I wanted to focus on memory portion in a serious way, so at least we walk away with some understanding. Let me just go to the last slide, and Ami, if maybe some other time I can talk about the storage, which will be fine. So let me just go back to the objectives. So we touched upon the memory optimized table from the index structures, and I think we know that memory optimized tables must reside fully in memory, and there are good monitoring tools available to see how memory is growing and shrinking in the garbage collection. So that's pretty much where it is, and we will talk about storage at some other opportunity. Thank you so much.
Thank you very much, Sunil, for an enlightening presentation, and I think that it will be a very good idea to maybe bring you over again to talk a little bit more in depth about storage. I'm sure there are fascinating aspects to that as well. So with that, I would like to thank all of you who attended this session. Just a reminder, in a few days it will be uploaded, the recording will be uploaded to our website, imvc.sqlpass.org, and we hope to see you in next month's session. So till then, have a wonderful, wonderful weekend. Bye-bye.